Hello, everybody. We're going to be going over free response questions for Unit 2. There are two in this section. And so we'll be taking a look at how forces act on different objects and how we can describe those forces with free body diagrams and what happens when these forces act on a system. Okay, so I think I might wait here for maybe another minute just in case people are signing in. In the previous sessions, I did give you guys time to work on them. At least the free multiple choice questions. I think for the free response, it's worth a try trying to get ahead and do them. But because this is considered like a 25-minute question, I think in the interest of y'all's time, we'll probably start working through these relatively quickly. And I would like to give you guys time to think about them. For instance, if time allows, try to do the other questions ahead of time in the future. That way, when you guys sit here for the review, you just can kind of sit back and see and compare what you did with the like, I guess, correct approach or the answers. So it is 6:01, and so I think we'll go ahead and begin here.
Sir,
Yes,
is
sir.
this unit 3 which progress check is this, sir?
This is Unit 2, and then it'll be the free response.
Thank you.
No problem. Okay. So this is a long free response question. Chances are this one's going to be about 25. And let me zoom in a little bit just because my hand feels like it's moving too small for what it's writing. Okay. So it's going to be about a 25-minute question. And so they tell us block 1 is resting on the floor with block 2 at rest on top of it. Block 3 at rest is on a smooth table with negligible friction. So the coefficient of friction here could be thought of as being 0, which is a multiplier of the normal force so that we can get the friction there. But it will be 0, so 0 times the normal force will give us 0 or negligible friction. Really, I should say approximately equal to 0. It is attached to block 2 by a string that passes over a pulley, as shown above. And the string and pulley have negligible mass. So here, the rotational inertia of the pulley is going to be 0. The mass is essentially considered to be 0, and its size and friction are also not important. Same thing with the string. So question or part A here, or part 1 of part A really, reads, on the dot that represents the block, draw and label the forces. Really important. Generally, you do not want to draw components on free body diagrams. So they're telling us here, yeah, don't draw the components, just draw the full force. Exerted on block 1. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So this is the point mass approach, where that entire block size doesn't really matter. And we really just look at the center of the mass, and we draw the forces extending from the center of mass here. And they want us to draw the relative lengths of all arrows to reflect the relative magnitudes of the forces. So in here, they don't necessarily tell us which blocks are going to be more massive than others, but we can go ahead and estimate by size that block 2 is less massive than block 1, and maybe block 3 and block 1 are of equivalent mass. So I'll give us maybe like a minute or two here just to kind of draw the free body diagram. What do you think the free body diagram on block 1 will look like when it's on the ground? We're going to want to keep track of the lanes here because that will matter. I'm going to assume most of us started with the gravitational force. So we have the force due to gravity. And I may actually make this a little thicker just in case it's a little easier to see. Okay. We do have the technology to make a straight line. Usually I feel like I fumble with this more often than not. For instance, here, this bad boy doesn't really start from the origin, but we can kind of fix that. And so something like this. And so here is the force due to gravity. And I went ahead and I drew it with 3 blocks worth of length. Now, if we look at this, the floor is going to be supporting this force here. Or it's going to be supporting this block, to be more precise. So we're going to have a normal force acting up from the floor. And I'm actually, now that I think about it, I'm going to make this guy a little bit shorter, and we'll see here why I want to make that a little shorter. I'm going to go ahead and make this guy 2 arrows in length. Now, because we have block 2 on top of block 1, we're going to want to keep track of the different forces here. And so this would be the force due to gravity due to block 1, but I'll just go ahead and just call it force due to gravity for now. Now, in this instance, we have block 2 pressing down on block 1 with its weight, which is why I say that the normal force here will actually need to be bigger than the gravitational force, because the floor is going to need to support essentially the weight of block 1 and the weight of block 2. Now, when I draw the force that block 2 exerts on block 1, we have to be careful, because normally people want to label it as the weight of block 2. But the big gotcha here is that the gravitational force of block 2 is not actually acting on block 1. It is the normal force. The contact from this surface creates a force that pushes down. So we're better off drawing this force and labeling it. Sorry. I think if I hold down shift, it will let me draw a straight line. Nope. And we just draw it off to the side here. Now, because I am limited to 3 squares here, I'm going to go ahead and just make this guy 2 squares and the other guy 1 square. So here we could call this the normal force from block 2, and this would be the gravitational force on block 1. So I'll just go ahead and label them like that. Fg1 is the weight of block 1. Any questions so far? So even though this force here, the normal force, is probably equal to the weight of block 2, we really don't want to call it the gravitational force due to block 2, because depending on this scenario here, this could change the value of this force here. For instance, if they were accelerating, it wouldn't be equal to the weight. So it's best to represent contact forces as the normal force. On the AP exam, is it fine if you put W1 instead of Fg1? Yeah, totally. Call it weight 1. You could even call it, like, let me just type the chat real quick, M1 times G. A rose by any other name is just as sweet, is generally the same here. And so for the weight, thankfully we can get away with calling it a couple of different letters here. Is it okay if we just call it the force of block 2? Yeah, totally fine. We can call it the force of block 2. So you don't necessarily need to call it a normal force, but that's traditionally how people would usually say it. But yeah, you could just call it F2 and then on the side say, yeah, that's the force from block 2. Now, if we look at the scenario, block 1 is not going anywhere. It's not going to change its velocity from 0 to some other number. So the forces here should be balanced. So the normal force from the floor, and here I'll go ahead and draw it with the shape tool. Here, that force should balance out those 2 downward forces. And so this would be the force, the normal force from the floor. And you could call it, you know, Fn floor. You could call it N floor. You could call it the force from the floor. The name's not too important. What I usually do is off to the side, I kind of define what they are. I'm more familiar with calling it with a normal force. Yeah, so that's fine. If you're more familiar calling it with a normal force, you can either use Fn or N. Any one of these titles is fine. You could call it F. I would hesitate to call it like F2, just because I don't think that's descriptive enough. Either one of these is fine. Why is the normal force of block 2 less than the weight? So really important, if we look at this, block 2 appears to be less massive than block 1. So we should expect the normal force here to be less than the full weight of block 1. We could, it doesn't have to be 2 squares. We don't know if it's exactly twice as massive. So we could have, we could make it, as long as we draw it a little bit longer, we are fine, okay? But we should hopefully recognize from the picture that they're trying to tell us that the weight block 1 is bigger than block 2. Okay. And so here, Fn from the floor is the normal force or the contact force from the floor. Any other questions? These are really good. From block. I'm sorry, the floor. Ooh, here's another one. Why is the normal force from the floor not the same magnitude as the weight of block 1? If I am this floor here, not only do I have to support block 1, but block 2 that is also on top of that. Even though the string here is drawn connecting it, we don't see anything pulling block 2 up because we don't see anything pulling block 3 this way. If we were to pull block 3 this way, that would tug on the rope and that would start to lift block 2. But because that's not the case, block 2 will be exerting probably the full like extent of its weight onto block 1, and the floor underneath it will need to support block 1 and block 2. Let me know if that answered your question. What about the normal force of block 1? Oh, so yeah, that's another very good question. Let me just put here contact. So another question here is, well, what about the normal force of block 1 pushing on block 2? So really important, when we draw free body diagrams, we only draw the forces that are acting on this block, that are external to this block. So when we draw the free body diagram for block 2, that's where we're going to show it. Because the only thing, like, kind of like I say, be the block or feel the physics. If you are this block, definitely you're pushing that other block on top of you. But we're only taking into account the forces acting on you, which would be like that block pushing down on you. Let me know if that answered your question there. And if I didn't answer your question, also let me know and see if there's a follow-up question or way I can answer that. For a free body diagram, we only draw the forces that are external to that object. Because we're drawing the free body diagram for block 1 right now, we only want to show the forces that are acting on block 1, not the forces that block 1 exerts onto the surfaces or whatever's near it. Other questions? Okay. All right. So I think that's it for the free body diagram here on block 1. There's nothing else acting on it as far as we know, so we'll go ahead and call it a day here. Now, if you notice, when I was drawing these two forces here, I kind of drew the weight acting exactly in the middle, and I drew the other guy off to the side. You're more than welcome to kind of put them like this, side by side, kind of both acting kind of off the center, because it is really hard to draw 2 arrows in the same direction. So maybe something like that. And so that kind of, this is fine. The way I had them before is fine here, like that. It doesn't really matter. But if possible, once I kind of have my free body diagram kind of finalized, I would kind of clean it up, maybe erase the arrows and draw them a little bit better here. Now that I know all the forces acting on it. Okay, so now we're going to draw the forces that are exerted on block 2. So again, we're drawing a free body diagram for the forces acting on block 2. Use the highlighter, I just realized. Okay. Draw and label the forces. And then each force must be represented by a distinct arrow starting and pointing away from the dot by the time I'm going to highlight the whole sentence. And draw relative lengths for the forces here. Okay, so if we look at block 2, we definitely see that it has weight. And in the previous scenario, because nothing, like I guess just because of the way I see it or the way I know it works is I drew the normal force from the contact of block 2 with 1 square in length acting down. Now here, the force that is pulling it down is the gravitational force. So we're actually going to label it the gravitational force or the weight. And so this would be the force due to gravity 2, where Fg2 or weight 2 or M2G, all of these are totally fine, represent the weight / gravitational force welcome. If you want, we are working on unit 2 progress check. So if you want, you can go ahead and sign into AP Classroom and then scroll down to the bottom of unit 2 and load that bad boy up. Exerted on block 2. And the thing that gives this thing weight is the Earth, so by the Earth. Okay, so there's our force pulling it down. Well, this block is totally balanced. It's not accelerating in any direction, so the forces, we need to have an upward force that balances this downward force. And so we're going to need one force pulling it up in length here. 1 square in length, sorry. And this is going to be normal force Fn. This would be, and let's see here. So it's going to be a normal force because it's sitting on block 1. So I would go ahead and call it the normal force from block 1 on block 2. So Fn2 or N2, sorry, 1, made a mistake right there. This would represent the normal force from block 1 on block 2. And you don't need to put these labels here, but I personally think it's handy to do that just to kind of keep track of everything. So do we have any questions so far? Yeah, so that's a really good question. Well, what about the tension in the rope? So as far as we know, nothing is pulling this rope up. If this were a hanging mass, I kind of drew this off in the wrong spot. But let's say for whatever reason, I happen to have a pulley and here's block 2, and then block 3 happened to be hanging here. In this case, block 3 is going to pull downward on the rope, which is then going to cause the rope to pull on block 1. But here, as far as we can tell, this is a frictionless surface. So unless this thing is actually pulled off to the side, we're not going to see anything exerting a tension that is going to lift this guy up. So in this scenario here, the tension is equal to 0. Let me know if that answered your question or if that makes sense. Okay, all righty. So it just so happens, and that's the big gotcha in this question. You could draw an arrow for tension, but I would say that your best bet is to either say that it's equal to 0 or just leave it off. Now, if you guys want, I'll share here with you all the scoring guide, just so that you can see kind of how they're looking for the answers here. Okay. So give me 1 second to load it, and then I'm going to do a new screen share. I was pulling up casts from Lord of the Rings. Let's see here, new share. So here we go. So this should be the warm-up. I mean, not the warm-up, the AP Classroom. Okay, so for part A, 1 point was awarded for indicating, oh, sorry, I'm on question 2. For question 1, part A. 1 point is awarded for correctly labeling the arrows for weight, normal force from the floor, and normal force from block 2. And so this is kind of how they drew it. They also happen to do 2 arrows here acting down. They labeled it FG1 and FN2 on 1. We don't normally draw the whole 2 on 1 part to it. We just kind of said, okay, that's the normal force from 2. And then we have the normal force from the floor on 1. And that's what this guy here is saying. This is the normal force from the floor on block 1. And this force needs to be the same length as those 2 added up. For section 2, here we had the normal force from block 1 on 2. That's what this guy here represents. And this is the weight of block 2 by the earth. Which can get a little confusing because here, if they're following their notation of who's creating it and who's it acting on, here it should say the force due to gravity on block 2, or really by the earth on block 2, but they didn't do that. So I think they're a little inconsistent there, but yeah, so it goes. All right, we're gonna go back to the OneNote. Okay, so any other questions on this scenario here? Okay. So they tell us in part B, block 1 is removed without disturbing block 1. Consider the scenario where the mass M3 of block 3 is greater than the mass M2 of block 2. Without using equations, make a claim about the motion in terms of balanced or unbalanced forces. So in the chat, go ahead and let me know if we remove block 1 here, is block 3 going to move? Yes or no? And then are the forces balanced? Yes or no? So in the chat, go ahead and let me know. Does block 3 move? Yes or no? Are the forces on block 3 balanced? Yes or no? Okay. All righty. Okay. And so just in case you wanted to see a diagram here of the scenario, or a picture of the scenario, not actually a free body diagram. Okay. So we got a couple answers here. All righty. So some people think it will move, some people think it won't move, some people think it's balanced, some people think the forces are unbalanced, and so block 3 does move because of the frictionless surface. Okay, so what's going to happen now? Well, because we remove block 1, the normal force from block 1 is gone. So this guy, and you don't do this on your free body diagram, but this guy's going to disappear because it's no longer in contact. That block is not there to support block 2, and it would fall. As it begins to fall, it's going to transmit a tension due to this scenario. And if I draw the free body diagram for the rope, there would be a tension going this way. There's a tension pulling up on the block. This would be like the gravitational force on block 2. So as block 2 begins to fall, it's going to pull on the rope. So actually, let me try drawing that here. And so now that block 2 falls and pulls on the rope, there's definitely tension acting in this scenario. Now, if we look at block 3, the free body diagram for block 3 is, well, we have the tension. This guy has some gravitational force. We'll go ahead and call it the gravitational force on block 3. This could be W3. You guys get the idea. There's a normal force. And these two forces are equal and opposite. But here, we could call it normal force 3 or the normal force from the table. I'll go ahead and call it table. So we're not supposed to show equations. But if we look at this surface is frictionless. So there is nothing opposing this tension here. So, because even though it's more massive, and that's the big, like, gotcha, they're saying this to throw you off. Even though block 3 is more massive than block 2, there's nothing for block 3 to like dig into. There's no friction to keep it from sliding. Kind of like if you were on a block of ice and you were fishing, like ice fishing, even the tiniest little fish could start bringing you towards the hole as it starts to tug on your fishing rod. So it doesn't matter how massive this thing is, all that tells us is that the acceleration is just going to be smaller for more mass. So it will actually move. And that's because the forces are balanced. Are unbalanced, sorry. In the horizontal direction. I probably should use the loop tool. So we can say there is no friction on block 3, so the tension on it is unbalanced. Any questions so far? Causing it to accelerate. And it'll accelerate to the right. Let me know if we have questions or we're kind of confused by that. And specifically, we could say causing it to accelerate from rest. So it's going to change its velocity. Its velocity is originally 0. It's going to be some number other than 0. It will move. All righty. Give me 1 second. If they give us, I'm going to assume block 2 is half the mass of block 3. So we have 3 counts of mass versus the difference. Oh, okay. Sorry. You're just, yes, I would say m2g is the weight causing it. Dividing it by the inertial mass of block 3 would give us the acceleration. I would agree. Okay. So now for part 2, we need to derive an equation for the acceleration of the block for any arbitrary values of m2 and m3. And we're going to express our answers in terms of m2 and m3 and physical constants as appropriate. So here you need to make sure that your answer has these variables to get full credit. So really quickly, let's look at our block M2. This bad boy has a gravitational force on block 2 equivalent to M2G. It has a tension acting up. And here, because it accelerates down, and you don't need to draw a free body diagram for this scenario, but it's in your best interest. Because it accelerates down, the downward arrow should be bigger here. And we're going to say it accelerates down. So when we make the equation for this using Newton's second law, so the sum of the forces on block 2, it will be M2G minus the tension equals M2 times A. And in this scenario, we could have left it as this, but they really want us to use these variables. So that's why I made this substitution here. So that's one set of equations, or one equation. The next one is going to be for M3. Give me 1 second. Space. I'm going to move this over. Let me know what we're thinking if we were confused, lost, or any of that good stuff. So this guy is just going to have the tension, and this guy's going to accelerate in that direction, to the right. And when we do Newton's second law, The sum of the forces acting on block 3, well, that's going to be equal to the mass of block 3 times its acceleration. And then we only have one force acting on it, the tension, equals m3 times a. And so here we have two equations. And we need to get the acceleration of block 3 in terms of these guys here. So we may be a little stuck. It's like, well, what do we do here? How do we get the acceleration of block 3? Well, the important thing to recognize is for this system, the system is going to accelerate together. M2 and M3 have the same acceleration. Alrighty, I'm picking up what you're putting down. They both accelerate with the same magnitude with acceleration a. This acceleration will be equal to the net force acting on both blocks divided by the mass of both blocks. Yes. So we can go ahead and think of this as a system. This is the long way. How do we of generating these equations? But we really could also think of it as a system of masses. And we'll talk about that approach here in a second. So what we can go ahead and do is, well, we don't really want the tension showing up in our equations. So we're going to substitute this expression here for the tension and then rearrange it. And we get M2G, and I'm about to turn all of these burnt orange into maroon. So give me 1 second, because my inner Aggie is seething with hatred. Not just kidding. But, you know, I'll go ahead and represent my homies here from Aggie land. See here, actually, can we get a maroon? I guess that'll do. That'll do, pig. That'll do. You guys have ever seen Babe the Pig? Oops, we could probably make it a little thicker. Whatever. Oh, no, let me change pens. There we go. That's probably too thick. Okay. There we go. Actually, I don't think that provides a lot of contrast. So this looks kind of like crimson. Yeah, never mind. Sorry for wasting y'all's time. Okay, so what do we do from here? We can go ahead and rearrange this monster. We're going to take M3A, move it over, and we get M2G equals M2A plus M3A. We factor out an A and we get M2 times G all over M2 plus M3 is the acceleration of the system and the acceleration of each block, because the only force acting on that system is the net force from these blocks, which is the weight of block 2. And then the mass of the system is M2 plus M3. It's the total mass of the system. So very good. A couple of you guys, or most of you guys, got this answer, so very nice. Any questions so far? Oh, yeah. Just go ahead. Okay, and I think my green may be a little too thick now that I'm scroll back down here. All righty, so far no questions. So describe in what way your part B is consistent or inconsistent with your claim. So we said, we claimed, or I claimed, the claim, oops, that block 3 would accelerate is consistent with the equation. Something along those lines. Was there another way to derive the equation, or what was that the best way? So here, because it accelerates down, right, the weight should be the dominant force. This is the greater force. So it's also the force creating this motion. So we'll say that's the positive one. That's why I did this part first off. Is there another way? So it's called the system approach, or what I call the block method. So if we look at this collection of masses, we have M3 and then M2. Sometimes what I'll do is something called the block method, and I just kind of draw a closed shape around my system. And I ask myself, well, so this is the system. And the system here has a certain mass. The mass of the system is M2 plus M3. It's whatever's inside this closed loop that I've isolated my system for, or that I've used to isolate my system. And we ask ourselves, well, what is the net force on the system? And so these two blocks themselves together make an open system where the net force is the weight of block 2. So this would be M2G. There's one force at this end of the blob, and that's the weight of block 2. Now here, there's definitely a normal force and a weight from M3, but we only consider the forces on the system in the direction of the acceleration. And the acceleration is going to be along this direction here. And so we usually can get very confused because forces are only ever, and accelerations are straight line vectors, but we just kind of ignore these because they don't interact with the direction of the acceleration. This end of the blob would not accelerate up or down, so we don't actually draw them. And then what this approach here kind of eliminates the tension in our equation. There was definitely a tension between them, but it's an internal force. And because that force is internal to the system, it'll cancel out. And it's not really an external force to the system causing it to accelerate. So when we do Newton's second law for the sum of the forces on the system equals the mass of the system times the acceleration of the system, we get the same thing as before. M2G divided by M2 plus M3 equals the acceleration. So that's the other way to do it. And this can be faster if you have a lot of ropes, but we usually kind of ignore that method, we kind of ignore this method here because it's lengthier, but it's good algebra. The tricky thing is to keep track of the acceleration directions, because here, even though the weight points down on block 2, that block is what yields this motion. So to kind of keep things consistent, we could say that down is positive, and if that's the case, this is the positive force and the tension is the negative force. We could do it where up is positive instead of down, but then here, this would actually have to be a negative acceleration because the acceleration is down. So you would need to slap a negative here to actually make it work correctly. The axis below, draw and sketch graphs of the velocity and the acceleration of block 2 after block 1 has been removed. You got to go eat? All right, have a good one. No problem. So the acceleration here, we saw it, there's an acceleration given by this equation. Now, as far as we know, the masses will not change, and the gravitational acceleration or field strength, G, will also not change. So it'll remain constant. Now, we said down was positive and it's going to accelerate down. So I would go ahead and draw an acceleration, something like this. And I really should draw it as a straight line. So give me 1 second. Really important, do not draw arrowheads on your lines. We don't know if this continues accelerating for infinity, which it doesn't. It's not an actual function. It's going to stop accelerating the moment it hits the floor. And so here the acceleration would be M2 all over M2 plus M3 times G. We change the color of that just because I don't think there's enough contrast there. Come on. Oh, I think my OneNote is crashing. Let me minimize it and then bring it back up. Okay, there we go. Let's change the thickness. Okay. Now the acceleration will be increasing. Now, if I have a positive acceleration, we can go ahead and say, okay, well, that's going to give a positive change in velocity. And if we start from 0, the velocity will increase in the positive direction, something like this. Any questions? We could have done these as negatives here. They actually won't care about the direction here. They just kind of want us to draw what should happen. They're going to be looking for a constant acceleration and a velocity that has a constant slope, because the slope is acceleration. And if one is positive, the other guy will be positive. If I have a positive slope, I expect a positive acceleration. If I had a negative slope, I would have a negative acceleration. Either one is fine here. Any questions? So this one did take a little bit. It's already 6:41. Man, time flies by quick. This is kind of one of the reasons why we don't really do these questions in this year, because our class is what, only like 60 minutes, 50 minutes after I'm done taking attendance and constantly going back in there to update the attendance for those people that come in late. So they do take a bit of while and explanation. And really, we could do these real quick, you know. Like in the AP exam, yeah, you'll have to do this in like 25 minutes, but you know, it's doable. All right, let me know if we have questions. Otherwise, feast your eyes on question number 2 here. We'll begin here in a minute. Just drink some water. So this is a short career response. It should hopefully go by a little bit quicker. And so 2 identical blocks A and B are on a horizontal surface as shown above. There is negligible friction. That's nice. Between the blocks and the surface of the block that the blocks slide on. As shown in figure 1, block A is initially moving toward block B, and they happen to have the same velocity. I'm sorry, the velocity of A is VA. I saw that as a B for some reason, and block B is initially at rest. Figure 2 shows the blocks in contact as they collide a short time later. In both figures, the location of the center of mass of the 2-block system is indicated by X, and that is labeled by CM. So here's the center of mass. Now we have learned how to calculate the center of mass. If this is X1 and this is X2, we can go ahead and get those distances to get the center of mass. Now it doesn't really matter here. What they tell us is that they are identical. So the center of mass is exactly in the middle. Oops, that was messy. Okay. So because we're talking about the center of the mass or the center of mass, and we're dealing with forces and collisions, we should probably be considering, well, how is that center of mass going to change relative to them? So because block A, and this is more for momentum, but just to kind of get the whistle wet and kind of gear towards the future, because this object is moving to the left, and this guy has a velocity of 0, the velocity of the center of mass will be the velocity of A times the mass of A plus the velocity of B times the mass of B. But mass B is at rest. Sorry, B. Now I'm getting cluttered here. I'm making a mess. So what's going to happen is all of this here is 0, and the velocity of the center of mass, all over the sum of the masses. Sorry. So what we find out is the velocity of the center of mass is ma all over ma plus mb times the velocity of A at the beginning. So if we notice, the center of mass is going to move to the right, and that's where it's at now. But if you notice, it's still smack dab in between them, and that's because they're identical masses. So just kind of like a little feature for the future. So in part A, on each of the dots, which represent the blocks as they are in contact during the collision, draw a single arrow to indicate the direction of the net force. So careful here, this is not a free body diagram. We have an arrow to indicate the direction of the net force. So off to the side, you may want to consider, well, what are the forces on block A? Well, we have the normal force on block A. We have the force due to gravity on block A. And then block B is going to push back on it. So we'll need to figure out how to represent this on the leftwardmost die, if any. So they want us to draw the direction, if any, for the net force exerted on each block. The net force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. If the net force is 0 for either block, write 0 under the dot representing the block. So if we look at this vertically, these guys cancel out. There's no vertical net force, and all we have is the contact from block B. So this would be the net force on A. Block B is going to push it to the left. So the net force will be that due to only to block B to the left. And let me know if we have questions here. By that principle, if we look at block B, again, there's some normal force on block B. It has some gravitational force due to gravity on block B. And then we have the force from A during contact. And so again, because these forces vertically cancel out, this object does not accelerate vertically, we are going to have an equal and opposite force. So let me actually try to do this guy. Oh, very nice. It knew exactly what I wanted. Exactly. So hopefully we're kind of getting to the idea that we're building up to when we talk about impulse. Let me just try to draw this a little bit more aligned to the center. Something that went a little too far. It's, I guess, snapping to grid. Okay, whatever. I think we get the gist. You know what? I think I changed the length of it. So I'll go ahead and paste a new one and flip the direction. I won't be able to, whatever. I think we get the idea. I'll just try to make it a little bit longer here. I think that matches. And so we could say the net force on block B is to the right. The next one, 2. During the time that the blocks are in contact, so there's some delta T here. Describe whether the center of mass of the 2-block system is speeding up, slowing down, or staying the same. So if we look at this, the net force on the system is going to be the net force of each of those objects on the system. So that's going to be the net force on block A plus the net force on block B. But we already recognize, because of Newton's third law, scroll over to the right here a little. These guys are an action-reaction pair. So the magnitude of the net force on A is equal to the magnitude of the net force on B. And they have opposite directions. So what we find out is that the net force on the system is going to be 0. So that tells us that the acceleration of the system is equal to 0. So the velocity of the center of system here is going to stay the same. So briefly describe in basic laws of physics whether the center of mass of the 2-block system is speeding up or slowing down. So the velocity of the center of mass of the system remains constant because the forces in the collision, there's a couple ways we can say this. The forces between the blocks are action-reaction pairs. Give me 1 second. And let me know if we have questions so far. Scooch this down here. And we could go ahead and just kind of leave this right here. Action-reaction pairs and are internal to the system. Canceling out. And let me just kind of move this here. So this is the secondary way to think about it, is the forces are internal to the system. And so whenever you have internal forces, you don't actually accelerate. That's where I say you can't cause it. Like there's this thing called, objects do not have self-action. An object cannot push itself to move. One reasoning for that is the objects, whenever an object pushes internal to a system, those forces are an action-reaction pair, and they will cancel each other out. And so the net force will remain 0. Okay, almost there. Last question. Wait, is that really it? I think I missed something. Okay. So now they're on an incline. The surface is tilted to an angle of 37 degrees from horizontal as shown in the figure. The blocks are each given a push so that at the instant shown, they are moving towards each other. Each block has a mass of 2.2 kilograms. Calculate the magnitude of the net force exerted on the 2-block system as shown above. So if we look at this guy, oops. Let me minimize this real quick. And go ahead and post a question if you happen to have one. Let's see here. Because each of these guys have a normal force. There's a component of our weight into the ramp, mg cosine theta. And this guy acting down the ramp, mg sine theta. So now in this scenario, they both have normal forces. They both have components of their weights that act into the ramp. mga cosine theta. B, mgb, there we go. And they have a component acting down the ramp, mag sine of theta. And sorry, this looks cluttered. Okay. So then we may be wondering, well, what the heck is the net force exerted on the system? So if we look at this, these forces cancel out. The components perpendicular to the ramp do not matter. All we really have in our system here, and we can do the blob method as before. So in my blob, I happen to have the weight of block B times sine of theta acting down, and the weight of block A, sorry, sine of theta acting down. Now, even though I drew this force inside the blob, it is not an internal force to the system. Here, the Earth is pulling on block A and block B, so they each feel an external force due to gravity that is unbalanced, and that's the component along the ramp. So what we get out of this is the net force on the system is MAG sine of theta plus MB times G sine of theta. And they tell us that the mass is 0.2 kilograms. The acceleration due to gravity, or the gravitational field strength, is essentially rounded to 10 meters per second squared times sine of 37 degrees. And then we're going to essentially double this because they both have the same mass. And so this comes out to 10 sine of 37. That's a 3, 4, 5 triangle. This is 4, this is 3, this is 5. Sine of 37 degrees is going to be 3 over 5, I believe. Actually, no, let's actually just kind of leave it at that. So what about the initial velocities? Do they come into play? Nah. They're just there to throw you off. They're not forces. Now, each of these velocities will change by the same amount because they each have the same blocks, or each of the blocks have the same force and the same mass acting on them. So what will happen is the velocity of the center of mass will be accelerating downward as these guys. Block B is going to decelerate on the way up, coming to a stop, and then block A will be speeding up towards it, such that the center of mass accelerates. Oops, I tried to write on my screen. Accelerates this way. If they're moving towards each other, then how is the net force on B pointing down the slope? Really important. They're not in contact yet. This is the component. Let me know if that answers your question there about the initial velocities, and then this part here, the second question here I'm answering right now. Component of the weight acting down the ramp. So they're not in contact anymore. That's kind of like the tricky thing. They came into contact with each other, and then now we have a totally separate situation presented by part B. And so sine of 37 is a number. Let's see here, 37 sine. Oh, I'm in radian mode, rip. I already forgot how to change this calculator from radians. It's like, this is an old calculator. This calculator is from like the 80s. But I don't use it very often, so I always forget when I'm changing between radians and degrees. Let me pull out another one. Oh, shoot, I pulled the batteries out of this one. Why do I do this? But if anyone wants to give me the answer here, I think it comes out to about 2.4. Don't quote me on that. I can't remember here.
Let me check real quick.
Okay, no, that's radians. Let's go to degrees. There we go. Okay, so 37 sine of this bad boy is 0.601, and then times 2 multiply. Yeah, that's 1.2. 2 kilogram meter per second squared plus 1.2 kilogram meters per second squared. Let me know what you get there. And so we get approximately 2.4 kilogram meters per second squared. And then let me see here. So for the and I'm trying to keep the names anonymous for the sake of like if I post it and I make it a public video, you don't feel like put on blast or whatever. So the person that asked, so what about the initial velocities? Where do those come into play? For the acceleration and the forces, they don't matter. What will happen is the velocity of the center mass right now is actually 0. at the very beginning, when these two have equal and opposite velocities, because these blocks have the same mass, the velocity of the center of the system is 0 for an instant. But because they're accelerating downwards, the center of mass will accelerate, changing the velocities of each of these. And let me see here if there's actually another part to this, because I think that might ask it. Yeah, okay. So here's the last question. So the last question says, at the instant shown in figure 3, that was this bad boy right here, the blocks are moving towards each other with the same speed of 0.35 meters per second. The blocks collide 0.5 seconds later, and they want us to find out what is the speed of the two block system's center of mass just before they collide. So there are two ways to do this. I think the easiest way here is the final velocity of the center of mass will equal the original velocity of the center of mass plus the acceleration times the time. So the velocity of the center of mass at the beginning is 0. You have, for instance, a positive 33.5 meters per second times 0.2 kilograms plus a negative 3.5. One's going in the opposite direction up the ramp, one's going down the ramp. It doesn't really matter here who's positive or who's negative because the masses are equivalent and they cancel out. So it's going to start out with a velocity of 0, and the acceleration here is going to be, let's see here. The force is this, the mass of the system, and I know we just ran out of time. I do apologize for that. If we take the net force on the system and divide it by the mass of the system, which happens to be 0.4 kilograms, 0.4. We can get the acceleration to be 2.4 kilogram meters per second squared all over 0.4 kilograms. That gives us an acceleration of 6 meters per second squared down the ramp. So that's going to give us a total acceleration of 6.4. And then, 0.35, sorry. Okay, I'll fix that here in a second. Thank you, appreciate that. I'm just kind of like hurrying now because I just saw the clock. This is half a second later. And so the final velocity of the center of mass after half a second, sorry. This is a multiplication. This is a 0.5. That becomes 3 meters per second. And so what will happen is one of these guys is going to gain like, let's see here. Another way we could do it is one guy is going 0.35. It experiences meters per second plus 6 meters per second squared of acceleration times 0.5 seconds. And then the other guy is moving up with a negative 0.35 meters per second of velocity plus 6 meters per second squared of acceleration. And so this guy's going to be going 3.35 meters per second this way. The other guy's going to be going, let's see here, take away 0.35 from that, 0.65, 2.65 meters per second up the ramp this way. Sorry, let me fix the other arrow. And so even though each of these blocks like have their own physics, then the acceleration of the center of mass here will be the same for both because they're both on the ramp and they both have the same acceleration. So if we see that one of them has an acceleration of 6 meters per second squared down the ramp, the other guy has an acceleration of 6 meters per second squared down the ramp, we add those two numbers and then we divide by the sum of their masses, and the masses cancel out, and we still get the same number for the acceleration for the center of mass here. Then we can go ahead and do kinematics, where it's the original velocity of block A and block B, and we do kinematics here. Except one's going to have a negative velocity, the other guy's going to have a positive velocity. And we can go ahead and say the velocity of the center mass. This is another way. I think this other way is faster. This would be 3.35 meters per second times 0.2 meters per second plus a negative 2.65 meters per second times 0.2 kilograms, all over a total mass of the system, 0.4 kilograms. And so we do this, let's see here, hopefully we get the same answer, because otherwise I'm a hack. All right, making a mistake, 2.65, 0.2 multiply, subtract, 0.4 divide, and so we get, I feel like I messed up somewhere. But I think I fat fingered something in my calculator. Either way, I think it's easier to just get the acceleration of the center of mass multiplied by the time, and then add that to the original velocity of the system, which was 0, because they're both moving in opposite directions with the same mass and same velocity. Okay, so I went over by about 6 minutes. I do apologize. Thank you for staying, those of you guys that could. Let me know if you have other questions. Other than that, I can show you guys here what the College Board was looking in terms of answers, but you're free to go if you'd like. Just show you here what they were thinking. So for part A, 2 arrows, we don't even have to label them, they just want the direction. So one pointing to the left for block A, one pointing to the right for block B. Section 2 of part A, they were looking for a point is earned for providing a valid description of why the center of mass of the velocity stays the same. The horizontal forces on the 2 blocks are a Newton's third law pair and are internal to the system. The net force on the 2-block system is 0, or there are no external horizontal forces acting on the 2-block system. So all 3 of those are valid options. You first saying it stays the same. For part B, we can go ahead and do the net force acting on 1 block, which is its weight times sine of theta down the ramp, 0.2 times 10 times sine of 37. And since there are 2 blocks in the system, the net force on the 2-block system going down the incline would be 2.4 newtons. And then for part B, section 2, 1 point is earned for substituting the correct values into an appropriate relation to get the acceleration. In this case, delta V equals A times delta T. Oh, that's why the velocity change is 3, not that the final velocity here is 3. Well, it just happens to be the case for the center of mass. But, and then for providing the correct answer, which is 3 meters per second. Okay. So let me know if you guys have questions. Other than that, we are done for today. I'll go ahead and stop.